Alrighty. So the other day, we kind of talked about similar versus congruent triangles, and we're not going to see many congruent triangles. You might see one or two more, maybe. But for the most part, we are focusing on triangles that are similar, and they have two very vivid characteristics. The first one is that they have equal corresponding angles, right? Those matching angles, those corresponding angles are equal to one another, which is nice. Now, similar triangles, what they also have equal is the corresponding side length ratios. And then what I said was, okay, like they don't have equal side lengths. No. If they had equal side lengths, they would be congruent triangles. Yes? But it's the proportion that is equal. So maybe we can just draw a little example of some like right triangles, right? We got one like that and one like that. Yeah? And we say, okay, 90, 90, and then we can say 60, 60, sure. So the way that we know these are similar, let me maybe pull out a calculator here. If we have, for example, 3 and 7, and on this triangle over here, we might have 9 and 21. Right away you can notice that there's something going on between these two triangles. Like the first thing that we see here is that, okay, 60, 60. Corresponding angles are equal. Oh, 90, 90. And right away that we know that they are similar triangles because of that angle-angle similarity. Yeah? At least that they have at least two angles, or at least two corresponding angles that are equal. We know that third angle has got to be 30 degrees in both of the triangles because all triangles add up to 180 degrees. So this one has to be 30, which means this one has to be 30. And that was angle-angle similarity, and that's what it's all about. And then we also notice that there's some sort of scale factor. Like to go from this triangle to this triangle, it's like timesing all the side lengths by 3. And then vice versa, if you want to go from the large one to the smaller one, it's that divide by 3. So the textbook might say that there's some sort of scale factor of 3, but what we say is that the corresponding side length ratios are equal. They're all 1 to 3 or 3 to 1, however you want to look at it. Now, a proportion, this is kind of what a proportion is. Like here's your 1 to 3 and then 2 to 6. It's kind of this, they're in the same proportion. It says here 1 out of 3 is equal to 2 out of 6. Because if you look, they just doubled the amount of yellows and then they doubled the amount of blues. And we can see that it's in proportion, very similar to how we can see it up there with the similar triangles. So it says here, when things are in proportion, then their relative sizes are the same. So you may have done this in grade 9. I know my grade 9s have been doing it a lot recently, at least. But when we're solving proportions, do you remember, like, it's like, oh, okay, yeah, we got to solve for x. Now, this is a proportion. This is saying x divided by something is equal to 4 divided by 10. Yeah? So we're right here. Now, some of you can look at this and you're really clever. And you're thinking, okay, well, actually, let's do it the equation solving way first. We'll have to solve for x, and x is currently dividing by 5. Okay? So how do we get rid of divide by 5? Multiply by 5. So we're going to take the x over 5, and we say it's equal to 4 over 10. And we're going to take this x over 5, and we're going to multiply it by 5. And whatever we do to one side of the equation, we have to do to the other side of the equation. Now, because we're dealing with fractions, I'm not just going to multiply by 5. I'm going to multiply by 5 over 1, right? Because, like, yeah, 5 over 1 is truly the same as 5. But I just want to write it as a fraction here because we know when we multiply fractions, it's probably been a while. Remember this? Numerator times numerator, denominator times denominator. when we multiply fractions. I know it's been a little while here. So we'll end up with something like 5x over 5 equals 20 over 10. And both of these reduce so nicely because 5x over 5 is just x. 20 over 10 is just 2. And x equals 2. Now that would be the real equation solving way of doing this. There's actually, I don't know, 4 or 5 different ways to do it. You might love it. If this is for you, that's great. Now some of you may have just, I'm going to do this way in blue. Some of you might have noticed this. Okay, to go from from 10 to 5, we're just dividing by 2. Yeah? So to go from 4 to x, we got to follow that same scale factor, just dividing by 2. And you might be able to, you don't do any of the math here. You might just say, no, I know it's 2. I know it's 2. Look what's going on here. That is certainly a valid way to do it, but it can get a little tricky when you're dealing with decimals and things like that, especially down the line with other types of similar triangles. And the last method that, I'm not much of a fan of, but it certainly does work, is called that cross multiplication. Remember that? Look, maybe we'll do cross multiplication in the example B. So we have 7 over 12, x over 48. So some of you are probably thinking, okay, 12 times something gives us 48, which means 7 times that same something will give us x. Or you could just say, no, I don't even want to think right now. 12 times x is 12x. 7 times 48 is a big number here, so 7 times 48, we get 336. And when we, the other one. And when we see that, straight away, we divide each side by 12. And x equals 28. Now, if that's for you, that's awesome. But again, there might be people out there that say, well, 12 times 4 is 48, which means 7 times 4 will give us x, and 7 times 4 is just 28. Yeah? So that's what I mean when I say, the other day I was saying, sometimes it's blatantly obvious what the scale factor might be. Sometimes it's not. You have to be a little bit careful. Now, another example of where cross multiplication is kind of our best friend here is when x is at the bottom. Now, when x is at the bottom, it's not that nice because usually x has been always at the top, and when it is at the top, we just multiply each side of the equation, portion, by the denominator of whatever x has. But in this case, because x is the denominator, it looks a little cringy. Like, ah. But what you're able to do, and what I do want to show you, because this is something that we're going to do in our next unit, is, well, I want x on the top. So I'm going to flip this fraction to be x over 1.5, which means I also have to flip this side here, which gives us 10 over 2. If you do to one side, you do the same thing to the other. In fact, you have to. And now that x is a numerator, we can go ahead and multiply this whole side by 1.5, and this whole side by 1.5. And truly what happens is, I know I didn't do it in this first example here, but multiplying by 1.5 cancels with dividing by 1.5. So you just have x, and I go right to my calculator and I can type it in just like that. 10 divided by 2 equals, and that's 5, times 1.5 equals 7.5. Yeah? It's a great method. Honest. It's really good. And again, x is on the bottom. You could flip each side, for sure. Or what you can do is you might like this. You might go, okay, 10 times x is 10x. And 15 times 8 is 120. Divide each side by 10. And then x just equals 12. Who likes that? Who's thinking, yeah, I'm going to cross these all day? Who's thinking, no, I like to flip it and then multiply by the denominator? Who likes to do more work? No one. Okay, so if we're able to solve proportions, if you thought that was pretty simple, that's half of solving similar triangles, truly. So here's an example. In this particular example, they tell us, they say, okay, here's triangle ABC, and triangle DEF. And they explicitly state that these triangles, they got this symbol here. Do you remember what that symbol in the middle means? What are they saying about these triangles? Yeah, they're similar. It's saying triangle ABC is similar to triangle DEF. So because it explicitly states that, we don't actually have to go and prove that similarity exists. But what they want us to do is first find the measure of angle C. Oh, I kind of missed that. Where am I? Find the measure of angle C. We'll do that. Okay, sure. And then what they want us to do is find the length of DE to the nearest decimal place. And yeah, usually we do just work with one decimal place. I know when we're dealing with a quadratic formula in the other unit, kind of wanted like 3 or 4 would be nice, but one decimal place for this stuff is great. So the first thing we're going to do here is solve for the measure of angle C. Angle C only exists in triangle ABC. So we'll say solve angle C. Write it just like that. Now, this is actually a pro tip for the rest of this course because we're dealing with similar triangles and more triangles in Unit 8. If you're ever given any triangle with 2 out of 3 angles, do yourself a favor and just get that third angle. It'll come in super handy at some point, I promise. We know that angle C is going to equal, well, 180 minus 121 minus 28. I'll go to my calculator here. 180 minus 121 minus 28. And angle C looks like it's 31 degrees. And that's great. I'm going to put that right in here. 31 degrees. Not bad, eh? Now, we're not shocked that that 31 is right over here as well in triangle DEF. In fact, if we wanted to, we know what angle E is, right? What's angle E? How many degrees? Yeah, 121 degrees, because it corresponds with angle B. And then that means angle D must also be 28 degrees, because it corresponds with angle A. Okay, next bit here. It wants us to solve for the length of DE. So DE, that's right here. It wants us to solve for DE to the nearest decimal place. Now what you can do is, well, you could put a little X here. I like to do that. It just reminds me, oh yeah, that's the one I'm solving for. Now because we know that these two triangles are similar, we know that their side lengths are in proportion, or the ratios of the corresponding side lengths are equal. So what we're going to do when we solve for DE, the first thing we're going to do is we're going to set up our corresponding side length ratios. And remember, the other day when we do that, you got to remain consistent. So I'm going to keep triangle ABC on the top, and then I'm going to put triangle DEF on the bottom. Just remain consistent with that, and everything will just fall into place so nicely. So this is where maybe a highlighter can kind of come in handy, or a different color. Because if we're looking at side length AB, we know that that's going to correspond with DE. And then BC corresponds with EF. And then CA corresponds with FD. Sometimes seeing the color there just makes it a lot more manageable. So side length AB corresponds with side length DE. And the ratio between them is going to be equal to BC over EF. And then we got CA over FD. So what we're going to do next is just fill in our blanks. So AB, we can actually replace it with 12.1. DE, we don't actually know. In fact, this is the one we're solving for, so we're going to put an X there. Now this ratio is going to be equal to BC. BC, we don't have anything, so I think we should just leave it as BC. And same with EF. We don't actually have anything, so we can leave it as EF. And that's not really helpful at all. And lastly, we have here CA, which looks to be 20.1 over FD, which is 16.1. Now, fortunately for us, triangles have three sides, which means that a pair of similar triangles will have three corresponding side lengths. Now, for us, we only need two of these proportions to put together and solve for the unknown, because all three of these ratios are going to be equal to one another. So truly, this middle one here doesn't give us any information. It doesn't actually help us. So we're not going to use it at all. So we're going to grab this first ratio here, the 12.1 over x, and we're going to set it equal to the 20.1 over 16.1. And when you look at this, you're like, yeah, I know what's going on here. So however you want to do it. I think a majority of us said cross, so we get 20.1x equals 16.1 times 12.1. 16.1 times 12.1. 194.81. We're close. Divide each side by the coefficient of x, which is 20.1. And then x equals 9.69. So we'll say 9.7 units. So we can go over here and say, okay, therefore, DE is 9.7 units. What do you think? It's not bad, right? Okay? Okay. Sample 2. It says use opposite angles and similar triangles to find missing measures. Okay. Find the length of FG to 1 decimal place. Now, this pair of similar triangles does not actually go in and explicitly state that they are in fact similar. So I have some helpful steps down here. One, the first thing here is we want to state the triangles. Yeah, okay, no problem. So we have triangle, what do you want to call this here? FGJ. And triangle IHJ. Those are our two triangles. And we have to prove that they're similar here. So if you look closely, we notice that angle G, right down here, must be equal to angle H. And the reason why is because they're both 90. So we can go ahead and say, all right, angle G is equal to angle H. And the reason for that is that they're both 90 degrees. It's kind of given. It's given to us. You can even write that, given. And what we could also state is that this angle J is equal to this angle J, because we will call that opposite angles. So we could say angle, let's call it FJG is equal to angle IJH. But really what we're talking about is, like, you could have written angle J equals angle J. And I would have said, yeah, I know exactly what you mean by that. And we can just say for here, the reason is that they're opposite angles. Now, I don't want you to write X pattern. I don't want you to write Z pattern or F pattern. I want you to write opposite angles, alternate angles, corresponding angles. So now we can kind of say, okay, therefore, triangle FGJ is similar to triangle IHJ by angle-angle similarity. We know that these triangles are similar because of angle-angle similarity. So we stated the two triangles at the very top. We have proven that similarity does exist. Now, because we're solving for a side length, we're going to now, step number 3, I suppose, is set up the corresponding side length ratios. So if you like steps, this is number 1, this is number 2. Number 3 is setting up the corresponding side length ratios. And before I go ahead and do that, I want to kind of match them up. Now, matching them up can be a little strange sometimes. I'm going to start here across from the 90 is yellow, yeah, and then again across from the 90 is yellow. Yeah, I like that. I think next I'm going to go across from the like this opposite angle. Across from here is FG, and then across from the opposite angle is IJ or HI. And then the last one is the last one. Whoa. Those colors. And that's a wonderful way to easily determine your corresponding side. It's like kind of strong arming those angles. Like across from that angle that matches has got to be, okay, perfect. Okay, now that they're highlighted, it's beautiful. It's so nice. So let's do, I'm going to start off with the green one. FG corresponds with IH. Okay, green one is done. Let's go GJ. GJ corresponds with HJ. And then the last one would be the yellow one. And it's JF corresponds with JI. Now I didn't write it, but notice that triangle FGJ side lengths were on the top here, and triangle IHJ side lengths were at the bottom. It has to remain consistent. Okay, that's where you kind of, like I would stop at this point, maybe like, okay, bang, and really make sure. I've even seen some students in the past, they go with a highlighter on here, and they're like, oh, yeah, okay, green, IH, is that the green one? Yeah, okay, good. All right, what's next? GJ is orange? Yeah, and they love this. They double check it all. Okay, yellow, bang. Because if something's wrong in this step here, you're going to be carrying out that mistake for the rest of the problem. Okay. What is the side that we're solving for here? Sorry, it's pulled down. FG. We can put a little X on FG. So FG is RX, and then IH is 4.3. GJ, we don't know. And the other one we don't know either. JF is 18.9. And JI 6.3. Lovely. Okay. Now again, we're in a situation where this middle ratio, I mean, it's not always going to be the middle one, but usually it's one of them that you don't really need to use. And we're going to rewrite this as x over 4.3 equals 18.9 over 6.3. Now, of course, you can use cross multiplication, but since x is already on the top, I'm just going to multiply this by 4.3, multiply this by 4.3, and you can just go into your calculator and go, okay, 18.9 divided by 6.3 is, oh, it's 3 right on. That's pretty cool. Times 4.3 is 12.9. So bang, bang, x equals 12.9. There's no units again. Okay, so we'll say therefore, side length FG is 12.9 units. Set up the side length ratios and use a complete ratio and a ratio with a variable. Yeah, so this is what we would call, here, maybe we can put it in yellow. Like this is, that's the completed ratio. Both things are filled in. And this is the ratio we're solving for, right? And it only has one unknown. So of course we use those two when we're solving for the unknown side. Folks, questions? It's not bad, right? It's pretty good. It's fun. Okay. Example 3, this is the last one here. In the diagram, DE is parallel to AC. And they put in these little arrows to remind us, yes, it's parallel. And it wants us to find the length of AC. Now, it doesn't explicitly state that these are similar triangles, so we're going to have to go ahead and prove them, that they're similar. So do you see the two triangles that we're dealing with here? Do you see them? That's why the first rule here is to state the triangles, or first step, rather. I see big triangle, big one here, ABE, right? The big one there. So we have triangle ABC and triangle DBE. It's that little one just above it. When you state them, it's a lot nicer. Seems like a redundant step. Like, why are we doing that? But trust me, if you didn't do it, you'd be like, oh, it's strange. So now we have to prove why they are similar. Now, 99, I shouldn't say 99. I'd say 8.5 times out of 10, you're going to use angle-angle similarity for the absolute very most part. You're always going to be using angle-angle similarity to prove that they're similar. But there are a few that they're not going to give you any angles. There's not going to be parallel lines. They're going to be separated, and all you're going to have is side lengths. Very similar to that example from that last example we did yesterday. But for these ones, seeming like it's angle-angle similarity all day. Anyone see an angle that they know for sure are equal, a corresponding angle that is equal? Yeah, B. Angle B is equal to angle B. And the reason for that is because it's a common angle. They share that angle. In fact, when you write the triangle, they both, notice how they both have a B in there. They both have angle B, the same one. And we have a ton of these patterns going on, right? See that F pattern? So we can say, all right, bang, bang. So we can say angle, we call that BDE, which is really angle D, is equal to angle BAC, which is really angle A. And those are equal, what do we call the F pattern? Do you remember what type of angles they are? It's not alternate. It's not opposite. Is it? Perfect. Corresponding angle. Proof similarity exists, absolutely. So because of that, we can say triangle ABC is similar to triangle DBE by angle-angle similarity. It's almost like here's our statement, and here's our proof, or our reason. Okay, we are looking for the length of AC for the bottom. This one. So we're going to set up step 3. So this is step 2, step 3, setting up our corresponding side length ratios. I like to follow the alphabet here because I know that we wrote these out A, B, C, like in this sort of way. So when I say write them out, like A to B to C, we wrote the triangle out like that. And we wrote out the second one, DBE, on purpose DBE, because look, it follows the same sort of trend. Yeah. So when you're setting up your corresponding side length ratios, this is great because you almost, when you really get good at this, you won't really have to look at the triangle if you've done it correctly. But I always confirm, always confirm. So I'm going to start off with triangle AB. Now, again, maybe I should write it. I'm going to do ABC on top and DBE on the bottom. I'm going to keep that aside here. It's not really part of anything. It's just to remind us, okay, this is what's going on. AB corresponds with, check this out, like if you look at the way the triangles are written, AB corresponds with DB. Okay? Equals, and it truly does, you can see it on the side. The next side length is BC. BC, we can almost assume it's going to correspond with BE. And it does, right? BC, BE. You see it? It's really nice. Then the last one, CA, corresponds with ED. So we kind of did CA corresponds with ED. So writing it out in a very particular way, in order, following the same sort of trend, is super helpful. Okay, we're going to go ahead and fill in the blanks here. AB, from A to B. How long is it from A to B? Do you see it? Yes, here. See, that's from D to B is 48 centimeters. We're looking for A all the way to B. Yeah, 60, because you're thinking, okay, the 48 plus the 12, 60 centimeters. So be careful of that. They might throw a couple of those at you. So we got 60 centimeters over DB, that's the 48. BC, we actually don't know. Oh, it's the middle one again. And BE, we actually don't know. CA, or AC, is our X. And then EB is our 36. That middle ratio will not help us at all. We grab these, 60 over 48 equals X over 36. I'm going to multiply each side by 36 because I know that cancels with that. And then it's just up to my calculator here to help me out. 60 divided by 48 is some nasty number, times that nasty number by 36, and we get 45 right on. Alrighty, therefore, I'll do that here. Therefore, CA is 45. Is there units this time? There is 45 centimeters. Okay. We have a good chunk of time here. There's some good homework here in the textbook, and notice that I put this worksheet part here. Now, I'm not going to give you that worksheet today because if you remember, tomorrow will be our work period. So This one here, I'll give it to you tomorrow. But for right now, we are working here. And number 11's got 2 stars around it because it's kind of tough. It's kind of a tough one. Questions at all? It's not bad, right? It's pretty good.